Okay, so good afternoon, everyone. Happy World Quantum Day to everybody. Yeah. Yeah. There's not only mathematics days throughout, there are also quantum days. Yeah. So my name is Francesco Petruccione. I'm the director of NITheCS. I'm also a quantum guy, so it's really a big pleasure for me to welcome you here today. And we have a team of two speakers. Yeah. Professor Barry Garraway, who's standing next to me, and Professor Menica Dibenedetto, who will speak after Barry. Yeah, let me introduce both of them in one go, and just for streamlining things. Yeah, Barry is a professor of physics at the University of Sussex. He completed his undergraduates at Oxford and his PhD in Manchester, and he started working in quantum optics back then when it was not so mainstream as it is today. Yeah. And over a few stations in Helsinki at Imperial College in France, he ended up being professor at the University of Sussex. And he's been working in this area for a long, long time. Yeah. The second speaker, Menica Dibenedetto, has been working on this for less time for obvious reasons. Yeah, yeah, she's based in Maastricht. Yeah. And she did her undergraduates at the University of Bari in Italy, where she's originally from. Her PhD in Aachen, and over a few postdoctoral positions, she ended up at university in Maastricht. Yeah. Menica has also an MBA, yeah, so she's really multi-talented, yeah. But I don't think she will speak about that today. Yeah, and this combination I think would be very useful because Barry speak about uses many years of working in this area long before it became fashionable. Yeah, if I can say so. Yeah, yeah. And Menica is a new entry who only knows about the fashionable side of things. So it will be a very nice to see different point of views on the same topic. Yeah, but Barry, people are here to listen to you and Menica and not to me. So please, you're most welcome to start with your talk.
Thank you very much. Thank you for the invitation to speak here. It's a great privilege and pleasure. Okay, so let me get the volume right. Quantum technology. First of all, I wanted to just have a quick couple of slides about where I'm from. So UK, the University of Sussex is based in Brighton, so basically straight south of London. And at the moment, we're probably close to this kind of level of greenness, and this is the sort of university campus here, and this is a very typical architecture of the campus that I have there. And this is atypical architecture in Brighton. A structure called the Royal Pavilion, which is in the Indian style, and of course the Brighton Pier, which is known to many people. So a few half familiar features maybe. So I'm going to start by just talking briefly about Werner Heisenberg. He's part of the reason why we're having this International Year of Quantum Science and Technology. So when he was awarded his Nobel Prize, he was awarded it for the creation of quantum mechanics. That's a very important thing to create, but it wasn't something that he really did on his own. But 100 years ago, this year, there was a sort of step change in the design of quantum mechanics, and as a result of that sudden change in what was happening in quantum mechanics, we're honoring it right now. And that had a lot to do with Heisenberg's trip to this island, which is off Germany. It sounds like a fantasy island, Helgoland, but he actually just went there to escape the pollen in the mainland, and that enabled him to think a bit about quantum theory. But as I said, he wasn't the only person to think about quantum theory. There were people like de Broglie. He was interested in matter waves and also got a Nobel Prize for working on those kinds of things and showing that matter and particles could have a wave nature as well as a particle nature. So I'm telling you this is the kind of prehistory of where we are with quantum mechanics today. And he was involved in these kinds of discussions about the future of quantum mechanics, as was Pauli, of course, famous for the Pauli exclusion principle, as well as some other Pauli effects, which meant that whenever he went inside a laboratory, apparently something broke in the lab. That was one of the things that he was known for. And then there is Niels Bohr, towering over everything with his philosophical thoughts, which were sometimes difficult to sort of refine, but he had a very important role to play in the development of quantum mechanics at that time. So now I jump. So this was all in the early years. Now I jump uh, uh, up to roughly well, 1989 was when the Nobel Prize was awarded, and the characters that we have here are Norman Ramsey, Damelt, and Powell. The latter two people on the right were involved in trapping ions, charged particles. So they were developing the first traps to hold those things. That's something that's very important today because one of the designs of quantum computers involves holding charged particles, or these ions, in position in traps. But Norman Ramsey devised a key principle for making atomic clocks work. And without the work that he had done, we wouldn't have the precision in time that we have today. So this was work that was completed in advance of 1955 when the world's first atomic clock was produced. You can see it's quite a large object. Atoms are produced at one end and go in a beam across to the other end, and there's an interaction with microwaves which has to happen to make the clock accurate. It's large, and it's at the time it was cutting edge technology, arguably quantum technology, because quantum mechanics is involved in the interactions with the microwaves as the atoms go through. Fast forward to today, and this is the sort of atomic clock that is being tested in America right now, the so-called NIST F4. It's another cesium atom thing, but nowadays the atoms are launched at the bottom and they go up in a fountain. That's why it's called a fountain clock, and then fall down and are interrogated again with microwaves at the bottom. The principles are very similar, but you couldn't operate this clock without the development of laser cooling and trapping and the methods for slowing down atoms, which is what was developed to avoid having this kind of beam. That means you can have a very short interrogation time. A typical beam like this would have speeds of about 300 meters per second, and give you a very short interrogation time over a distance of a meter or two. But with the fountain clock, when you launch it up, it just is the same as a tennis ball thrown up a meter or so, and you get a couple of seconds of interrogation time. That's important for getting a much higher precision in the clock. However, that's today. This was 1955, and what for me is potentially a turning point was the development in 2004. So now we're quite recent of this chip scale atomic clock. So it's a really miniaturized atomic clock. It's not going to be as good as this NIST F4, but it is still very good. You can see here that it says that it will lose 1 second in 300 years, if I remember rightly. It's covered by the screen there. Yes, 300 years. So that's the level of accuracy this really small clock has. And I'm going to come back to that in a few slides' time. The clock was farmed out to a company, and I'll return to that story in a minute. And this is a really modern version of the chip scale atomic clock. This is the 2019 version. It's much more accurate than this one by a factor of about 1,000. And here you're comparing it to the size of a coffee bean, just to give you a sense of scale. This one is the size of a grain of rice, apparently. So very small things with impressive accuracy. So this clock is at least as accurate as the clocks, or it's more accurate than the clocks currently being used for GPS in orbit. So I said that cooling and trapping is very important for this level of precision. I'm just going to very quickly run through some Nobel Prizes, which is one way of sort of highlighting key landmarks in the development of the necessary quantum physics. So this was the 1997 prize for the cooling and trapping of atoms down to maybe several microkelvins of temperature when held in a vacuum. And then in 2001, we had Bose-Einstein condensation, which goes to even lower temperatures, so sub-microkelvin, even tens of nanokelvin, and that was in 2001. And in 2005, we had a split in the Nobel Prize. This second half here, these two people got the Nobel Prize for the development of the so-called optical frequency comb, which is a way of linking, can be used now as a way of linking microwave-based clocks to optical-based clocks. So you can connect different types of clocks with different frequencies using these combs, which are combs in frequency space. But particularly would highlight the Nobel Prize going to Roy Glauber here for the development of optical coherence. So optical coherence is very important in the development of the laser, even though this Nobel Prize came quite late in the story for him. We had Nobel Prizes for the manipulation of atoms and ions, single atoms and single ions. Back in the early days, Schrödinger even wondered if that was possible to manipulate individual atoms and ions, or if it was sensible to talk about that. And we ended up with Nobel Prizes for forces from light. So this was, without forces from light, you would not be able to cool atomic beams down to being nearly stationary, for example. So that is a quick survey ending here with the Nobel Prize a couple of years ago, going for the development of entanglement. So I just quickly run through those. Now, I said in the title, this is a sort of personal view, and it maps out the development, how things went in time, and I'm going to talk about how quantum technology started in the UK. Maybe there's something useful from the story to learn for the development of quantum technology in South Africa as well. Maybe, maybe not, but maybe you can learn something about it. I go back to the story of the chip-scale atomic clock, and I just want to mention, as I do, because you see there can be other devices surrounding this device, and I want to mention that the transistor, for example, first made in 1947, could be regarded as a kind of quantum technology if it was invented today. The idea of quantum technology now is kind of, I think it should be a bit flexible in terms of what you do with the quantum theory in terms of putting things out there for industry to make. I mean, so the quantum technology philosophy is, let's take laboratory scale quantum physics, which sometimes is involving very large optical tables or equipment, as far as possible, shrink it down, make it something useful to people, something that you can maybe put in a truck or carry in a suitcase or put in your mobile phone. This is the direction people want to go with the technology, to make it more useful and to do new things. And we'll touch on some of those things. So, retrospectively, you could call those things quantum technologies if you want to. The chip-scale atomic clock, and I mentioned it already, was, in a sense, without using the phrase, was a quantum technology, because it was the miniaturization of the atomic clock, retaining excellent accuracy as you do so. And the interesting part of the story is that this development, which happened in NIST in America, was then thrown out into a company. So a company was formed to further develop it and then market it. And this is kind of setting the pattern. Before the real quantum technology revolution happened, it sort of sets the pattern for the idea. Take academic ideas of quantum things that could be useful, put it to a company, let them develop it, market it, hopefully eventually sell it. That's what happened with this clock. So I'm very suspicious that although this is 2011 that it happened, that this influenced people who were thinking about these things in the UK. So just 2 years after this company was formed, by the way, now it's been sold off to a much bigger company, but so you don't find it. Just 2 years afterwards, and after some lobbying of government in the UK, so Sir Peter Knight, for example, was heavily involved in doing this lobbying, there was a government announcement, 2013. So they've decided to boost quantum technologies research and donate to research £270 million, I guess roughly 200 million American dollars, let's say, as a ballpark. But notice the little sort of thing, the little sort of catch is coming. So 190 million pounds of new money. Okay, so some of this money was old money being rebadged, so being moved from something to something else. But the minister at the time said that it's a major opportunity, and the logic that was at the time, and I think it's still there really. What the logic was that the UK should be trying to develop cutting edge technologies and not trying to compete on old technologies with other countries like Taiwan or China or wherever. It's a bit like if you go back a few industrial revolutions, you know, should we be trying to do textile production in Manchester when other countries in Asia are doing it so cheaply? It's difficult to do that. So what we need to do is compete on the cutting edge technologies, invest in those and do well at those new technologies when we can. And this was part of the logic that was expressed back then in 2013. So how did that develop? Well, a year later, so time marches. So you see this is 2013. So it takes 1 year before they form these research technology hubs and now notice how the money shrunk a bit. So now it's down to 120 million. So some of the money went somewhere else. So the 120 million now goes to these topics, which have kind of set the scene for other places as well. So we had a hub in sensors and metrology, a hub in quantum enhanced imaging, so using imaging methods, for example, to look round corners using light that bounces around with timing information in it. Networked quantum information, which also included the quantum computer program, and quantum communications, which includes, for example, quantum key distribution or cryptography, so quantum secured cryptography between two people, for example. So those were the hubs that were set up, and this is another aspect of the philosophy behind these hubs. This is relating to this graph. So the hubs are meant to destroy this dip in the graph. What is the graph? It's called the valley of death in technology development. So along the x-axis here, you have what's called the technology readiness level. And technology readiness level of 1 means that basically it's fundamental research in an academic institution. Yeah. Okay, somewhere like here, for example. If it's 2, then it's getting a bit more towards being a device. Somewhere around 5, 6, you're getting prototypes. You're thinking about you maybe making something that can be marketed, and you make prototypes of it, and then you are refining prototypes, typically with commercial development and hopefully making a product by the time you get to TRL 10. But the problem is, typically, there is a gap between what research funding can do to think of making an innovative new type of technology and commercial development taking over. So the industrial companies picking up this new idea, developing it a bit further, and making it in the way they can make it rather than the way academics can make it, and then going through the marketing process and everything. So there's a gap here, and a lot of ideas are seen to die in this gap, which is somewhere in the middle of the TRL levels. It's also true that there's a gap in funding in this area, government funding to support it. So there's a lot of government funding and other funding as well, of course, at the research level. Commercial funding available here, but a gap in funding at that level. And the idea here was with the hub activity, to boost this funding and try and flatten this curve a bit. So that's the valley of death. So now I talk about a few of the topics, and I must monitor the time just to check how I'm doing. I'm not going to say much about quantum computers. It's a very popular subject, and a very interesting one, but I know that I have a general audience here, so I can't go into the detail of any quantum physics, but happy to talk afterwards. Basic idea is to go from bits to quantum bits. I should make you aware there are multiple ways seen of doing that. So, for example, so-called superconducting qubits is one popular method, and as I already mentioned, trapped ions is another popular method, and there are other methods as well. And the issue with it is that it's the same issue as with Schrodinger's cat. You may have heard of Schrodinger's cat. Here we have a picture of a ghostly cat living in the quantum world, which is part alive and part dead. And this problem is that you don't see that, you don't experience that Schrodinger cat thing in real life. We talk about it, but it's not something you experience, and that's because the decay mechanisms fight that and destroy it, and this kind of being both on and off at the same time doesn't happen. But inside the quantum computer, when you talk about something much smaller than a cat, like a qubit, the quantum version of the bit, then that can be in a superposition. But these decoherence mechanisms that kill the cat, well, so kill the superposition of the cat being dead and alive, they will also destroy quantum bits. And it's a constant battle to design things that are robust against those decoherence mechanisms. I'll just say, and this is an important point, quantum computing is a quantum technology, but quantum technology is not all quantum computing. Sometimes people talk about quantum technology as if it were synonymous with quantum computers. It is not. They are not the same thing. And even our own MPs in Parliament, I noticed, are confused about this issue when I listened to one of their special sessions about quantum technology. So a quantum computer is one type of quantum technology, and actually it's one that's very far away from having its applications, but there are very profound applications. So one of the potential applications when they would be working fully is that it can crack this encryption algorithm, RSA, which is used by a lot of banking still. And if that's cracked, then your banking transactions are not secure. Curiously, quantum mechanics has the cure for that problem, which is to use quantum key distribution. But that's another story that comes in a minute. So this is where you end up with a paradigm shift, and that's where it's important to take action. If the relevant quantum technology is developed, then there has to be a response to a working big quantum computer. So it's hard to do. So this was Oxford's development idea to build a UK quantum computer, announced in 2014, and I think they planned it to be working in 2020. And it's like many of the quantum computers, it's not really there at this point in time. It doesn't reach the initial ambition, but they made a lot of progress and have interesting results about that. What's happened now in the UK, so just jumping forward a bit, 10 years actually, is that we now have a national quantum computing center, looking a little bit like this, I think, artist's impression, where they aim to test all the different platforms for quantum computing and make it a hub for quantum computing research. Okay, I put this in as a joke slide. Not far from University of Sussex, there actually is this shop called Quantum Computers already. And I took the image here from Google Street View to actually see this thing. So I guess that just means that quantum is becoming a popular name, and that's one of the things that you have to be careful of. Everything that's labeled quantum is not necessarily quantum. I can almost guarantee that this shop has nothing to do with real quantum computers. University of Sussex, though, is trying to build a quantum computer, and this is an image from Hensinger's plan for doing that. I won't dwell on it because there are other competing methods as well. But the idea is that these balls represent ions that can be moved around in the network into zones where they can have quantum logic processes applied to them using lasers and magnetic fields, and then you move these qubits around to other places for more logic, and you do a computation that way. But this is still experimental at a very small scale. I briefly mentioned quantum key distribution. It's nice to mention that here, because South Africa was one of the early public users of it. So it goes back to this World Cup event in 2010, where quantum key distribution, which is a key part of quantum cryptography, was used as part of the World Cup for some communications Francesco down at the bottom there will know much more about that than I do, but I just thought it's important to mention it. What I gather they used there was a quantum key server. This is 2015, which it was developed already before the real quantum technology revolution started. So people were already using cutting-edge quantum technology to make commercial devices. And ID Quantique was the company that developed this. I think this is the second version, and it's basically a device looking like a computer, but it enables you to do quantum key transmission, and those quantum keys can be used for secure classical transmissions later on. It's a way of getting the secret information from one place to another. Within the technology hubs that were developed, one of the hubs was wanting to make a quantum key distribution device which would fit in your mobile phone. So the idea is that, for example, in communicating with a bank terminal, you don't need to physically insert anything in the terminal, and you can have quantum secured communications with that terminal to look at bank balances or ask for cash or whatever. So this is the imagination, and they have made a lot of progress in developing that over the years. Quantum, I won't spend too long on this, but quantum key distribution did get criticized by classical cryptographers. Here we see the results from the National Cybersecurity Centre in the UK, and they were criticizing it. They said that it has some limitations. Thinking about the software side of it in that, it's only addressing part of the security problem, so not the storage of keys, but the transmission of keys it addresses. And they think that there could be unknown types of attacks. Of course, there always are. I think the real problem here was that at that point in time, the quantum cryptographers were not really talking to the classical cryptographers. Since this report was made in 2016, there's been a lot more engagement of the two types of people, and I gather that it's a more sort of satisfactory situation at the moment. 2016 was also the year that the Chinese launched a satellite for quantum communication with the satellite in orbit. This particular satellite, I gather, is now has now burnt up, probably in the atmosphere, and there's a second one up there, and I think Stellenbosch had a role in communicating it recently. So that's an ongoing thing, and one of the things that impressed me with that is not just that they did it, which stimulated pretty much a lot of Europe to try and do the same thing, but also that it's simply a part of their 5-year plan in China to do this kind of thing. It's nice to have this kind of forward thinking in terms of cutting edge technology. So the sensing is the sort of work that I'm involved in, and we have quantum sensors for gravity, gradients of gravity, magnetic fields. I mean, the gravity sensors are so sensitive that people can think of making a gravity telescope, it's called. The gravity telescope could potentially detect human beings moving around inside a house from the street, let's say. There's sufficient accuracy for that. And that starts to raise ethical concerns about the development of some of these technologies. With new technologies, there are always new ethical questions, and this is an example of that kind of thing. Magnetic fields, rotation time, quantum imaging, they're all possible things in sensing. A number of universities were involved in this sensing project. I won't dwell on that more, but also I want to point out a number of companies, so lots. A lot of these companies, and this is a feature which is quite typical, a lot of the companies wanted to be involved in the development of this research project simply to have an eye on the cutting edge research. They wanted to be inside. They're not necessarily actively doing calculations or making things. Some of them are, like E2V and M squared is making lasers, but others are just watching and waiting to see what happens. And it's a lot of companies that were involved in that. Right, I mentioned quickly some applications in magnetic sensing. So one aspect of magnetic sensing is to use Bose-Einstein condensates to probe things like batteries. So there's a lot of interest in, I guess, in electrical engineering, in how batteries work and how the currents are actually flowing in batteries, especially as they sort of go towards end of life. And we can map that out using these Bose-Einstein condensates. It's a kind of magnetic microscope. We have various types of more accurate magnetometers than exist in the market at the moment. And we have a potential replacement for this device. So this is what you might use for magnetic sensing of currents which are flowing inside the brain. And it's a very cumbersome, large device which can be replaced by well, these are simulations that show that there's a tenfold increase in accuracy, but this was what the prototype looked like. Basically, you put a helmet on, and then you have sensors plugged into these slots here, which are quantum sensors and are more accurate and can build a picture of how currents flow in the brain. And I saw recently this more recent picture from the Physics World magazine. And children are one of the targets of this kind of magnetic sensor because they move their heads around a lot. They tend not to stay still. So in the older types of sensors or MRI or whatever, it's a problem to image any problems in the brain of children. Here you put the helmet on and the sensors move with their head. So that's one development. There's a lot of development of clocks. I'll just go quickly through that. The main point is, again, making them smaller, as with the chip scale atomic clock. So compact ideas are good. This one, you can see it's on 30 centimeter scales, a 14-liter volume package, hopefully not too heavy. So size, weight, and power are things that people are interested in. You want low power, low size, low weight when designing these things. And that's the sort of thing that they're aiming for. So portable clocks, generally of great interest. Just say a few words about the gravity sensors. I mentioned the gravity telescope. I mentioned here the gravity sensors which already existed as quantum technology developed. So these were already products that were available from companies like AO Sense and Muquans, which has now also been taken over, so it doesn't exist anymore. But they already made these accurate gravity sensors. And these sensors, and the Birmingham version of them, so the Birmingham one has a double gravimeter set up. So there's like two of them, one on top of the other to deal with fluctuation problems. This sensor can detect not just potentially people moving around in buildings, but it can detect voids under the ground, for example, as well as mapping what gravity is doing. It can find old mine shafts and things like that, for example. This is their sensor being trundled out of the university. That's the official photo. And this is the photo from one of my children who just happened to be walking past one day and saw this and sent me a WhatsApp saying, "Is this the gravity sensor?" And yes, it was. So he saw it moving around there. So underground mapping. In Britain, we have a big problem knowing where all these cables are going under the streets. Nobody quite knows exactly where they are. So one of the applications of these gravity sensors is seen to be mapping where these street cables are. You often can't use ground penetrating radar, for example, if it's very damp soil, as it tends to be in the UK. So it's useful for that and for checking foundations. And they're also now using this gravity sensor to, for example, map gravitational fields in the ocean and testing it to be part of a quantum navigation system for navigating, which is a desirable thing in case we lose GPS completely due to some malevolent action. And also in situations where you have jamming or spoofing of GPS, which is a worry and is happening. So, for example, in Eastern Europe, there is jamming of the GPS signal, which causes problems. Well, minor problems, but it causes problems for the aircraft who realize then that they can't use GPS when that's happening. So here it was being tested on a ship. So I want to mention some more practical issues. So, and this was built into the projects that were doing quantum technology development in the UK. Pay attention to the supply chain side of things. Actually, supply chains have been mentioned a lot recently with the tariffs business going on, and the tariffs business is upsetting supply chains. But it's also true that if you're developing a new technology and you're needing new components, you need to have a supply chain for the new components that you may need. You may need to have new laser diodes to cool atoms and things. You may need new small vacuum chambers. You may need new bespoke magnetic shielding to make everything small, for example. And there have to be people to make these things because they're all specialist things. Now, I briefly mentioned that once the UK quantum technology movement got going, it went into Europe. So in 2016, Europe emitted a number of ideas for developing quantum technology of its own. And a few of these reports came out from the EU, and they adopted this structure, which is basically focusing on very similar things to the UK: communications, computers, simulation, which we relate to computers, and the sensing aspect, magnetic fields, gravity, rotation, and so on. So it was done in a very sort of similar way. However, this is the organization of the European effort. Very complicated, I would say. Uh, so back to the UK. And we had a report in 2016, which was just after everything started, looking at what are the potential opportunities. It has a lot of detail in it. I recommend it, but I just make the conclusions here, which are interesting. So quantum technology, it's a new way of working for some academics like me, but it's a way of working that I find very interesting. It may benefit society, but it's hard to quantify or predict. I think there will be benefits for sure, but you are never quite 100% sure. Closer interactions with industry are good, and we hope that public and funding agencies will not be disappointed by what the academics will do. So quantum technology, since the beginning, has developed with phases 2 and phases 3. I'm not going to go into the detail of that, but I just mentioned maybe that the flagship involved 1 billion euros. Okay. But we see a bit more about the funding effort on this plot taken from 2021, where you see the UK investment at $1.3 billion, and then there's separate European countries, so Netherlands, for example, at nearly $1 billion, Germany at $3 billion, China, huge $10 billion, and America at that point, $1.2 billion. So a lot of money going into quantum technology development. If we fast forward to 2024, this is the chart, we can see South Africa here. Great. So it's good to see that. You may not be aware of it. I don't know the details of it, but about $3 million going into the quantum technology program here. America's now at about $5 billion, and the UK at about $4.3 billion. So it's very interesting to see how it all has developed, but I haven't got time to say more about that. This is just to mention that a bit like the problem of the supply chain, the development of technology is complicated. There is a lot of different pieces of research going into just the iPhone, for example, and a lot of it coming from DARPA, research agency in the US, Department of Energy in the US, Army Research Office in the US, and so it goes on and on. US military, US Navy, all developing different things that actually in the end became part of the technology that became the iPhone. So it's expected to be a similar story with quantum technology developments, that actually there'll be bits and pieces in some cases coming from many places. I noticed that just last year there was, or maybe a bit before, there was the development of a European quantum industry consortium. So industries involved in quantum getting together. And I was staggered by the number of new companies. So there is a huge rate of startup companies. And this consortium has 190 members from European countries. I can pick out a couple here. So this one is Universal Quantum, which is Sussex based. And down here we have the National Physical Laboratory of the UK, for example, involved in this consortium. But many companies, and at this point, I'm no longer recognizing the names of the companies. There's so many now developing. I don't know them anymore. In the old days, one did, but it's going so fast. So a point about people near the end, as well as having a supply chain of parts, we need a supply chain of people if quantum technology is really going to develop. So there is a growing shortage of graduates, PhDs, and people with postdoctoral experience. We need more of these people to really encourage the development of the quantum technology industry. At least we need engineers and people who are quantum aware. So have some basic training of quantum, so they have an idea of what's going on without necessarily knowing all the detail, because those people will work on the engineering of products that have to be made and use their engineering or electrical engineering knowledge, depending on what's involved. And of course, you need systems engineers as well to make systems that are going to be usable by people in the end. So this tends to get forgotten, but it's truly essential. And so if you're going to boost your quantum technology program, you need to have an enhanced program for producing PhD graduates, for example, to work on the quantum side of that, as well as the other people. Okay, so I was going to talk about some of my work, but I'm suspecting that I'm a bit over time now. So I will do that super fast, if not at all even, looking at the time. So, but basically, recently one of the highlights of my work was to ensure that an experiment got on the International Space Station, and the relevance of that is that the same things that are being done on the space station can be these are the space station results, but it's just atoms floating in space as far as we're concerned here. It can be part of something that can be developed on the ground, which is to make very small chips which have a huge amount of the stuff that you need to run an experiment on an optical table compressed into something that's on centimeter scales. So it's a different kind of chip. It's an atom chip, but with lots of added parts. And this idea was thought up already in 2011, so some years ago. But you have things to make the vacuum, you have things to move the atoms around or trap them, and you have things to detect the atoms and to make some kind of device. In my case, the device that I'm interested in is a rotation sensor, and this shows the development of plans to make the rotation sensor with microwave units and conductors that fit around it and so on. It's a complicated device, but that's part of the project, which is part of a quantum navigator. And we simulate, for example, atoms moving in these circular waveguides, but I'm not going to dwell on that. The conclusion I'll leave you with, I think, are those of the Blackett report. We hope that at the end, the public and funding agencies will not be disappointed. And there I finish. Thank you.
Yeah, thank you very much,
And
Barry.
apologies for running over time.
No worries, no worries, no worries.
Yeah.
Maybe while the second speaker sets up, we have time for a few quick questions. Anybody wanted to ask something?
I have one
Yeah,
question.
please.
So, as I understand that the quantum technology based on the fundamental principle of quantum mechanics. So, regarding the gravity sensor, whether this principle of quantum mechanics will modify in presence of gravity or in particularly the presence of strong gravity?
Yes, and there's different scales of the modifications that can happen, but basically, if you have a cold atom and it's moving at low speeds, then gravity will change the trajectory of that atom. So it won't go in a straight line, but maybe some parabolic trajectory.
Mm.
Or if it's in one of these traps that we make, the gravity will pull it down and shift its location. So gravity has those subtle effects. In terms of the gravimeters, that's all accounted for. It's part of the way the device operates, so that's built in.
So how this modification manifested at the level of quantum theory? I mean, whether this
Yeah.
modifies the uncertainty principles or some in other ways.
Yeah, so the gravity, for the most part, there's different ways of separating the problem. For the most part, the gravity supplies a trajectory for a moving atom, And as a major approximation, you can assume that the atom follows the trajectory, but it has its quantumness in the excitation of its internal states, which is a bit like a qubit in a way that it's can be in one internal state or another one or a superposition. And that's what's manipulated in the gravimeter.
But how we can talk about the concept of trajectory in quantum mechanics, because it is completely probabilistic theory.
Yeah, no, I mean trajectories are subtle, but there's a regime where trajectories are appropriate. There's other regimes where you must have matter waves. And I also wanted to add that people are designing tests with objects, small objects, tests of whether gravity itself is quantized by looking at future experiments, which are very sensitive, to see if the effective quantization of gravity is responsible for some of the decoherence that we have in quantum systems. But that's a cutting edge research project rather than quantum technology.
Okay, thank you.
Yeah.
I think our second speaker has set up.
Okay.
So maybe we can.
Mike.
Yeah. Maybe you can help with
Mike is
that operation. Here we go. Thank you very much, Barry. We will have maybe time for a few more questions at the end. Okay, so Menica, I think everything is set up. Over to you. Thank you very much.
No. Okay, now? Okay, now it's better. Okay, so I have kind of 23 minutes. So I will try to make it in 23 minutes. The title of my talk, it's very catchy, right? It's Brain on a Quantum, but don't be, let's say, disappointed by the fact that we are not to put any brain on any quantum, but it's a way to say that maybe somehow we can do that. And this, at the end of the talk, I will explain a little bit one of the projects I'm working on that could be the first step to put the brain on a quantum. So the field in which we are is called quantum neuromorphic computing, that basically bring together machine learning, neuromorphic computing, and quantum computing. The overlap is called augmented general intelligence, but I will not talk about that because I don't know how to give a definition of augmented general intelligence. So let's see one of these parts one by one. So we have the quantum computing. Actually, we didn't talk a lot about quantum computing. So I will just spend a few words to give you, let's say, the basic notion that maybe you will need. So let's say that the three important words, actually five important words of quantum computing are entanglement, superposition, reversibility, fragility, and measurement that I forgot to write there. So entanglement means, as you can see here, for quantum computing, as Barry say, we are not using the bit, but we are using a quantum version of the bit, which are basically a quantum system, a quantum entity. And they are important because they can be entangled. So this means that we can create a kind of, let's say, kind of relation between two quantum bits. They can be superimposed, as you can see here. So they can be of two colors at the same time, somehow, depending how much percentage of one color you have, one yellow color or blue color you have, you can have a kind of superposition situation with these quantum qubits. They can evolve according unitary evolution. This means that you can always reverse this evolution of the qubits, but they are very fragile. So they are when they interact with the environment, they basically, the quantumness of this entity disappear. So this kind of characteristic make the qubits very unpleasant for computation, if you think, but actually you can do things with a quantum computer because you can exploit basically the entanglement and the superposition superpower. So machine learning, I think everybody is aware of this name. So it's the art of taking all the data that you have, try to think about some good algorithm that can maybe do some prediction on taking decision, and it is widely used nowadays in different sectors. Neuromorphic embrace the idea that the morphology and dynamics on the biological neuron somehow matters. And neuromorphic computing, as quantum computing, is another technology that you can use in order to perform computation. And neuromorphic computing in particular is an energy efficient way to enable machine learning through a synergy between the software and the hardware. So this is the field where we are. So this is, let's say, what I want to talk about today. But before to talk about that, I just want to so we are here to celebrate the UNESCO Quantum Year. I just want to look at lately to the Nobel Prize in Physics from 2021 to 2024, and somehow there is a very hidden fil rouge in this kind of Nobel Prize. Sometimes it's very clear. For example, if we saw the Nobel Prize in 2023 for experimental method that generate atomic proof of, the other one, 2022, for experiments with entangled photos, establish the violation of Bell inequalities and pioneering quantum information science, you can read the word quantum there. But actually also the other prize somehow, if we narrow it down, they can be related to some quantum mechanism. And today I will briefly talk about the one given 2020 first for work on climate modeling complex system and disordered material. In particular, in the work of Giorgio Parisi that offer a kind of solution to the for solving spin glass models, and the last one given last year to Hoffield and Hinton for the foundational discovery in artificial neural networks that have shaped the development of machine learning. So somehow these two prizes are related with the idea that I'm gonna give you just at the end of the talk. So if we look at, let's say, the recent Nobel Prize, I think it's worth to mention the interdisciplinary nature of the work that they did, and also the fact that they were kind of driven by curiosity in order to answer to big questions like how minds work. And I think somehow this, let's say, I like the interdisciplinarity of this prize because make you understand how it's important to look at something from different point of view. Indeed, if you look at the interview from Hoffield, so he basically, we are not going to read it all, but basically, if you want to understand how minds work, for example, right, you want to understand how minds work, but he ended up to build up a machine learning model, which is called Hoffield neural network. But the driven question was how minds work. And if you want to answer this kind of question, first thing that you need to do is to narrow this big question down in simple question that you can afford, that you can try to give an answer to them. And also, you need a mixture of different point of view coming from physics, chemistry, biology, and this kind of project, this neuromorphic quantum computer related project, really is coming from a multiple perspective on the brain, let's say. So few words about this spin glass model. They basically explain the interplay of disorder and fluctuation in physical system from atomic to planetary scale, and can be considered as a generalization of the Ising model that explain the ferromagnetic behavior. So if we have a spin model, basically, you can imagine a system, and each element of the system is described by a spin. The spin can be up and down, and then you can associate basically an energy to this system that is simply given by this form, considering only the interaction, the neighbor's spin. Now, you can also change the coupling strength of this interaction. Somehow, you can add a weight to this multiplication, but also you can add an external field, so your energy system that you can associate to this will have extra term. Now, this is the simple kind of Ising model, in which basically we have we consider this spin that can be plus or minus 1 or 0 and 1, but the spin glasses kind of are still kind of very similar to the Ising basic model. But what changed here is the fact that you have structure, which is, let's say, kind of crystal structure. This spin here are somehow aligned in a way that is not ordered like in the spin glass model. They can be something like this. And then the interaction, of course, there are different ways of choosing the interaction between the neighbor spin somehow try to bring the system to a configuration that corresponds to the minimum energy that we can associate to this kind of system. And at one point, so for example, this interaction will try to put the system in this situation. In the spin glasses, there are some problems because this kind of, you can have some effect that can disturb, let's say, the convergence of the system to the minimum of the energy. And this kind of let's say disturbance come from, for example, the geometry or some impurities that we can have. For example, in this case, where we have a triangle, let's say, configuration, in order to have, let's say, the relation between these two spins good for reaching a minimum of the energy, this spin should be down, but this will enter in a kind of frustration with the spin that is down here, because then they will be both down, and they are both down, so the elements that contribute to the energy will just put the energy to a higher level. So what does it mean? That this kind of system can be quite complex to study because you can have kind of same low energy associated to multiple configuration of this spin. And the energy landscape that you end up with, it's very rough. Of course, the nature reaches the minimum in a natural way, but if you want to put this on a computing or studying it with, from a mathematical point of view, it's a very difficult problem. It's called NP-hard problem, which means, in simple words, that it's very difficult to solve, very difficult to find the minimum energy, and it's also very difficult to test if one proposed solution is the solution of your problem. So, based on this idea of this kind of Ising model, Oldfield proposed this neural network, which basically take the name of the inventor, and also we add the contribution from him with the Boltzmann machine. Both of them are cases of recurrent neural network where you have the nodes which are all-to-all connected. So I will go very fast here because I think I have just 2 minutes. Okay, but I will just to summarize. So basically both Oldfield network and Boltzmann network are energy-based model in the sense that you can associate to this network an energy value. And in one case, in the Oldfield network, what I want to mention here is that the update of the weights is happening following a learning rule, which is called Hebbian learning rule. And this Hebbian learning rule coming from, let's say, the neuroscience field. And what this rule says that if you have two neurons in this, or two nodes in this network that are both active at the same time, then you strengthen the connection between these nodes. Otherwise, the connection became weakened. And the nice things of this Oldfield neural network is that basically you can train the network in reaching the minimum energy of the network, and this minimum energy corresponds to a pattern that the network was able to memorize. So this means that when you have in input some, let's say, an image that is a bit corrupted, this network is able to recognize what is in this image because somehow has this memory effect inside. So it's able to reconstruct the image you start with because of this Hebbian learning rule. And the Boltzmann machine are just let's say, generalization of the Oldfield neural network where the nodes are basically update following a Boltzmann distribution rule. So in this case, we have basically a stochastic, a probabilistic version of the neural network. And so why I'm talking about this? Because this kind of model, Oldfield neural network Boltzmann machine, that are basically models that are using machine learning, but they are coming from physics, and in particular statistical physics and solid state physics. Plus, the whole field neural network use a particular learning rule that helps the network in having this memory effect. But the topic I introduced to you is about quantum neuromorphic network. So because we would like to put a brain on a quantum, and the way we can do that are really up to you, to the researcher. You can do in different way. One of those, for example, would be what classically has been done is try to use some classical learning paradigm using in neuroscience and put in a machine learning. So, but we would like to use the quantum technology in order to put the brain on the quantum. But first, we need to understand what is the brain. And the brain, it's a complex system. It's one of the most efficient computing machines because it can perform a lot of operation, of course, with using very little energy compared to classical or quantum computer. And this characterized by this vast connectivity. So it's made of this macro area, each one with a specific function. But you can study the brain at different level. For example, you can look at the long-range interconnection between these areas. Okay, you can narrow it down and look at the microcircuits, at the column of neurons that you can have in each of these nodes. Or you can even narrow down your, let's say, your focus and look at the single neuron or how the neuron communicate through the synapses. Or more, you can look at the neurotransmitter that are released, for example, in the synaptic class, or you can look at the protein dynamics that are embedded in the membrane of the neuron or inside the neurons, or even at the genetic level. So basically, you can study the brain from different perspective. You can use for each of these boxes different tools. You can use, for example, the behavior of the human originated by brain functioning at, doing some behavioral experiment at fMRI level, or you can probe the brain with, EEG or any kind of technological tool, or even look at the dynamics of the protein using different kind of theory and experiments. So the neurons are very different. Each one has a specific function, function and shape, and they can really be, they are very highly interconnected. And if we look a little bit at the structure of this cell, we know though that the information is processing and arrive to another neuron because, let's say, the axon connected to the dendrites of the following neuron. So, but how the information is processed in the synapses. So basically, we have a kind of electrical pulse that arrive in the cell that triggers some chemical reaction. So we have release of neurotransmitters in the synapses, and then we have the propagation of the signal in the following neuron. So it's a very complex mechanism, right? So this kind of mechanism originates the spike, that each element, each part of the spike really is related to some action, something that is happening at lower level in the cell. I will just go. So depending on what are you looking for, we can use different kind of models of the single neuron. We can go for a more biological inspired to a kind of perceptron style, where just look at, let's say, at the activity of the single cell, if it's spiking or not. So there are a lot of single neuron model. They are they have a variety of model that can be used. Some of them are very close to the biology, other one are very artificial, and how to solve them is also, so more close to the biology, the model of the neuron is more prohibitive is from the computational point of view. So let's say that we can have three kinds of generation of neural model, from the simple perceptron one to the one that act a nonlinear activation to the integrated fire type. And today, this is, let's say, the overview of the old single neural model that you can use. I will just spend a few words about the Hatchclay-Huxley model because it's the one that will come later. So I will go a bit fast on that. So basically this kind of model, it's one of the more close to biology, is characterized by the explicit, let's say, formulation of the dynamics of the channels that open and close during the spike production, and can be also represented with these small circuits. So each channel is basically associated to a kind of resistor, and then is described by this coupled differential equation where the change of the voltage over time is basically related to the dynamics of the 3 ion channel, the sodium, potassium, and chloride. So I will just mention here, but it will come back later. And this kind of model, it's quite powerful, because even if it's a bit difficult from the computational point of view, put it in a network, the single neuron is able to produce different mode of the neuron, of the activity of the neuron. So now that I talk a bit all this kind of single neuron model that exist in the world, it's important to put them together, because the true powers emerge when these neurons are interconnected, so they can form our brain. And so how can we pass from the neuron to the circuits? So we can choose any kind of single neuron model that I just presented before, and we can put in a network. But depending on which kind of model, then you can end up with a different type of network. And the big two blocks are the spiky neural network, which are more neuroscience driven, use a lot of neuromorphic computing, that are more close to integrate and fire kind of neuron, and artificial neural network, which are more used in computer science, and they are, let's say, more, they just reproduce, let's say, the spike as it is, as a signal. So example artificial neural network, it's, for example, this is a feed-forward neural network. So you have some input layer, hidden layer, output layer, and then basically each of the layers became active or not active depending on the way it's connecting with the previous layers. And you can have some neural activation function in order that can be a Boolean function or a discrete function that can give you, some classification of regression outcome. The spiky neural network are a bit different from artificial neural network. And the main difference is, for example, first of all, they can have very complicated structure. They are not made in layers like the artificial neural network. And the dynamics that originate when inputs arrive to the input layers of neurons can be quite complex. And as you can see, the amount of spike, the amount of spike that you obtain, it's very sparse, but the time at which they happen are very important. So basically, there are two big paradigms for artificial neural network, and the spiky neural network in particular are more close to the biology reality, because they can use single neural model that really can also represent the dynamics of the neuron before the spike arrive. But the problem is that artificial neural networks are very advanced today, very good in, so there are a lot of technique for example, backpropagation, different kind of shapes of this neural network. The spiky neural network are a little bit behind artificial neural network, so there are not really good optimization process for spiky neural network, but they look promising when used in a quantum in a neuromorphic setting. So, what the brain does. So we look at the network, we look at the neuron, and when we put a lot of neurons together, they form this network that is able to learn something. The learning is basically the process of acquisition of memories. And the memory is the ability to store, retain, and recall information. Now, the learning in the brain is basically related to the ability of the synapses between neurons to change their strength. And this is called synaptic plasticity, that underline the brain plasticity, but is not the only way of learning. And also has been also shown that actually, in order of a network to grow and in order to a network to be able to learn, you don't only need neurons, you also need all the environment around the neuron. for example, some cells that are called astrocyte or glia cell. They are fundamental in the learning process. But if you look at all the neural network theories or the learning technique that are used to train the neural network in computer science, the rules of these cells are never represented in the model. So also the learning process somehow is kind of simplified when used in this computational model. So there are different learning paradigms. I will just spend a few words. I already talked about this Hebbian learning rule that has been used in the half-Hilbert neural network. But there is also another learning rule which is called spike timing dependent plasticity, in which really matters the time at which the spike arrives and the difference of time of spiking from the pre- and postsynaptic neuron. So once we put everything together, we choose our single neural model, we choose the network we want to use, and we define which kind of a learning rule to use. All these three can be up to us. Then, in order to make this neuromorphic, we need a device to add. And the device that can be used in neuromorphic computing are of different kind. And I will just talk about the memoristors that are the ones that are most used for. So the memoristors is a resistance with memory, and it has been basically introduced theoretically in 1971, so it's quite recent. And the first, let's say, attempt to create practically this device has been in 2008. So the memoristor changed its resistance based on how much current has moved through this device. For example, in the classical, let's say, classical resistance, we have this linear dependence between the voltage and the current. But in the memristor, we have this kind of behavior of the voltage versus the current, which is called hysteresis. That means basically that when the currents arrive at a certain level, so when the currents increase, then we have a kind of swap between two working resistance of the model. So basically, depending on the currents, the resistance adapt itself, and at one point learn how to swap from one value to the other one. And this kind of device have been already used in machine learning. For example, here you have, for example, you would like to learn an image. So you have these 6 3x3 images that you roll in one-dimensional line. And we have this crossbar model in which each of these bar represent the gray value with a spike, and the spike is basically propagated through the bar and measured by the output neuron. And the propagation is happening here in these nodes where a memristor has been built. So the memristor, when you receive its input, give the output signal to the nodes here. And at a certain point, these nodes, this system is able to learn something. For example, you can have in output here the spike of each neuron. For example, if you look at the ability of spiking of the first neuron, you can see that the neuron spike only when the input is represented by this as this vertical line, or the second neuron is spiking only if you have this diagonal pattern in your input. Now, how to make this quantum then? You can build a quantum memristor. So a quantum memristor is so first of all, the resistance is a dissipative element in your electrical circle. So when you want to create it in a quantum memristor, you have to take into account that these elements dissipate somehow. So what you do, you can consider your system coupled with this it's called weak measurement scheme. Weak measurement means that you measure, in this case, the voltage in a weak scheme and a weak measurement scheme. So basically, when you look at the voltage, you do it in a very delicate way. So because we saw at the beginning, I told you that these quantum systems are very fragile, so they can really easily collapse and become classical. So you don't want to make the wave function described in the quantum system collapse. So you do a weak measurement scheme in order to only have partial information on the system, but good enough to measure out the voltage of the system. And in order to make this memristor, quantum memristor, let's say, good for the computational point of view, basically what has been done is couple the system with a buff, which is made of this oscillator, and this oscillator is related to different kinds of frequency, and these oscillators are able to basically keep all the energy that has been dissipated, and in this way, basically, we don't have a system that is irreversible, but still reversible. So we still implement a memristor here, but we keep, let's say, under control the dissipation aspect of the resistor. And this kind of quantum memristor basically show the same behavior of the classical one, and are being actually built in, have been, let's say, created using experimental, using photonic technology, and used in order to perform machine learning. For example, here you have this reservoir computing, in which some memristor have been used in order to, basically, the application was your image recognition. And let's say the advantage here is that the disadvantage here that you need to build up this quantum memristor, but the advantage here that you really don't need to have very complicated back propagation method or very complicated optimization process in order to optimize your model, because in this kind of setup, so you have this reservoir computer, it can be complex enough, but you don't touch it. What you train is only the measurement part that is happening at the end, the readout part. So I told you about the Hoffitt, the Hadgley-Huxley neural model at the beginning, because could be an interesting, let's say, attempt to create a quantized version of this model. How basically this work has already been done by basically substituting the resistor that we have in the Hadgley-Huxley model with a quantum memristor. And maybe once this thing is done, you can study you can couple one of these models to another one. So you can have a kind of oscillator made of these two quantum neuron, and look at the dynamics that this kind of system can generate. So basically, the idea is try to use this Hadgley-Huxley neural model, biologically inspired kind of model, and study it from with a quantum computational aspect, just substituting the resistor with the quantum memristor, and study it theoretically, but also try to implement it on using this photonic quantum memristor. So put it in an actual device, and maybe study, let's say, the performance for any kind of machine learning task. And the nice thing of this will be that maybe it's more sustainable than both quantum computing and classical computing in certain case, because you will not need a lot of energy in order to calculate to optimize the model. That is the most expensive part in a machine learning pipeline. So just to conclude, just 20 minutes over the time, with this sentence that the law of nature are written in the knot workings of our brain by this Thomas Etty, which is a mathematician from Pittsburgh University, and me in the knot part, because of course at the beginning I want to put the brain on a quantum. Yes, we can do that, but we need to go step by step. And one of those could be simply translating a model, an established model of quantum neuron in a quantum language, and maybe put it in a let's say quantum hardware that already exists, and maybe try to make sense of that. So this is my talk. Oh no, this is. Thank you for your attention.
Yeah, thank you very much, Menica,
Yeah.
for these very nice
Run a bit
insights on where the stories of quantum computing and quantum machine learning will end. Yeah, thank you very much.
Okay.
Questions for Menica? Zura, please. Sorry. Okay. I completely.
Thank you. Thank you very much. So if you have two neurons, are they ever connected with each other using two axons, or is it only unique? And if yes, then is that also something that shows up in machine learning?
No, in general, the information flow, so it's from
Only
the
one.
axon attached to the dendrite. But when you look at the overall picture, and then you have also this glia cell, this astrocyte, let's say this is a simplification of what is happening there. It's actually, it's much more complicated how the information is processed there. I don't know exactly what is happening, but I know that for sure there are some experimental work in which they see that the neural network does not grow in vitro if you don't add this glia cell. So, for example, another computational paradigm, so we have quantum computing, we have neuromorphic computing, but we have this kind of biological inspired computing. And this biological inspired computing, you try to build your, you grow your tissue, your cells, and try to see how information propagate through this cell in this made in the lab tissue. Yeah, I don't know exactly. I don't think we have astrocyte, no, but there are some weird way in which the information can be propagated. So what we look at are just model, and the model, yes, need to be simple for us to understand and to implement, but does not mean that they are related to what is really happening.
Thank you.
There are more questions or comments? Please, again, one there at the back.
Hello. Could you please clarify again what is the actual reason for quantum memory in the register?
In the register.
Quantum memory effect of what is the actual reason? What is the actual origin of quantum memory?
The quantum memory. Okay, but this is unrelated with what I say. So quantum memory. So I talk about memory as the capacity of the neural network that you need to have in order to learn something, and you have it is in human, but also you have it in the machine learning algorithm. You are talking maybe of quantum memory, so a device that in which you are hoping to store quantum bits, the so QRAM, no, the QRAM things. We don't have yet. We do not have a QRAM. It's just theoretically, let's say, plausible. Technology is not yet there, and there are maybe alternative techniques to keep the qubits alive. One of those, if, for example, is coming from quantum internet. No, you would like to connect different quantum computers all together, and one of the reasons you want to do is not really to transfer information, but basically to keep the qubits alive, moving it, because you cannot put somewhere and retrieve it, because once you look at the qubits and the qubit is gone.
Okay.
So
okay.
But there are different.
Thanks.
Any other question? Any other question for the previous speaker? Are there any questions from the online audience? Not so far. Okay, then considering that the NITheCS cinema will probably getting nervous because we're going a little bit over time. Can I ask Barry to join us as well so we can thank both speakers at the same time?